This is a problem that has baffled PhDs. It defies human intuition, named after a game show, and even today it still causes confusion amongst the cleverest of people. This is the Monty Hall problem. It's one you might have already seen, as it's pretty popular in many films and TV shows. Here it is in Brooklyn Nine-Nine.
Enough foreplay, let's get to the numbers.
It's the Monty Hall problem. Imagine you're on a game show. There are 3 doors, behind one of which is a car.
You're telling it wrong. There are 3 doors, behind one of which is a car. You pick a door. The host, who knows where the car is, opens a different door, showing you there's nothing behind it. Now the host asks if you'd like to choose the other unopened door. Should you do it?
No.
Yes.
It's simple math. It doesn't make any sense to switch. The prize is behind one of 2 doors. It's a 50-50 chance either way.
It's 2/3 if you switch.
So what do you think? Is it 50-50? Or is it 2/3 if you make the switch? Your intuition might initially tell you it's 50-50, like it doesn't make a difference whether we switch or not. But the correct answer is that it's actually very much in your advantage to switch, bringing it up to a 2/3 advantage. And in this video, I'm going to prove it with a simple visual demonstration using a technique I find makes this problem really easy to understand. I'm then going to do a working proof in Python as well. Now I'm going to show you a similar clip where this is discussed in the 2008 film 21, based on real events, which is kind of cool. Now, one thing that's interesting about this is pay really close attention to what the professor says about what the game show host knows. There's a really key bit of information that the game show host has, which I think changes the way you should be thinking about this.
All right, now, let's give Ben a chance for some extra credit, shall we? We're going to call this, the game show host problem, all right?
Ben, suppose you're on a game show, and you are given a chance to choose from 3 different doors, all right? Now, behind one of the doors is a new car. Behind the other 2, goats. Which door would you choose, Ben?
Door number 1.
Door number 1. Ben chooses door number 1. All right, now, the game show host, who, by the way, knows what's behind all the other doors, decides to open another door. Let's say he chooses door number 3, behind which sits a goat. Now, Ben, game show host comes up to you and says, Ben, do you want to stay with door number 1 or go with door number 2? Now, is it in your interest to switch your choice?
Yeah.
Well, wait. Remember, the host knows where the car is, so how do you know he's not playing a trick on you, trying to use reverse psychology to get you to pick a goat?
Well, I wouldn't really care. I mean, my answer's based on statistics, based on variable change.
Variable change, but he just asked you a simple question.
Yeah, which changed everything.
Enlighten us.
Well, when I was originally asked to choose a door, I had a 33.3% chance of choosing right. But after he opens one of the doors and then reoffers me the choice, it's now 66.7% if I choose to switch. So yeah, I'll take door number 2, and thank you for the extra 33.3%.
Exactly. People remember.
And just before we move on, why did the professor stare at the student like that? I find that quite funny.
66.7% if I choose to switch.
His little face at the end is just beaming like that, right? I don't know why I find that funny, but yeah. So this problem has been around for an awful long time. In 1975, a man by the name of Steve Selvin initially posed this question in a letter to the American Statistician, and it was actually then formally published a year later with the name The Monty Hall Problem, because it originally came from a game show where Monty Hall himself came on, and that was the challenge he gave to the contestants. And what's interesting about doing this formal publication is that it came along with a couple of different rules, which makes this problem really easy to simulate and test the results at the end. One is that Monty always opens a door which doesn't contain the prize behind it. Number 2, he must always give the option to switch doors. And number 3, which I think is the most important one, he always knows where the prize is. So fast forward to 1990, and then Marilyn Vos Savant enters the chat. And her name is particularly interesting because back at the time, she had an IQ score of 228. Now this was back in 1956, which at the time actually entered the Guinness World Records for the highest IQ, which is pretty cool. During her career, she ended up moving to New York and working for the Parade magazine, where she became a columnist. The whole point of her column was that people could write in with questions on academia, science, maths, logic, and effectively say like, hey, here's a problem, you're a really smart person, go and figure this out. So someone comes along, says, here's the Monty Hall problem, do you stick with the initial door, or do you switch? And then she rightly said, yeah, you switch. And following this, you might just think, okay, yeah, she's smart. She probably knows what she's talking about. I believe her. Maybe I'll go and try and prove it myself. No. Over 10,000 letters were then sent to the magazine. And I don't know how true or how reliable this is, but a report by the New York Times suggested that around 1,000 of those people, in their signature to go and complain about this lady's conjecture, over 1,000 of them had PhD in their signature. Now, I don't know if they've just put that on there to be smart or whatever, but I think this shows how controversial this problem is and how it quickly defies human intuition. Even though it is correct, you should switch doors, your intuition just tells you it doesn't make a difference, it's 50-50. So what I want to do is I want to show you a real quick demonstration using my screen share, and this, I think, makes the problem a whole lot easier. It's basically done by keeping the rules of the game the same, but you basically scale the problem up so it's much larger. The quick, real short version is, imagine you've got 10 doors, okay? So you've got, a 10% chance of it being in doors 1 to 10. Right, then we can say, go ahead and let's suppose we pick door 1. There's a 10% chance you've then gone and picked the correct door. There's a 90% chance it's in those remaining doors you haven't picked. So that's the way to think about it. It's what are the chances that it's in my zone versus the other zone. The other zone in this case, 90% chance there's 9 doors. Monty Hall is then going to open the remaining doors where, bear in mind, he knows where the prize is. So there's 8 doors he can open that don't contain the prize, and in that little subset of 9 doors, he's going to leave that one remaining door that has the prize. So let's say, for argument's sake, I've picked door 1, maybe the prize is in door 10, okay? So there's a 90% chance it's in doors 2, 3, 4, 5, 6, 7, 8, 9, 10. Monty will come along and say, right, I'm going to open doors 2, 3, 4, 5, 6, 7, 8. It's in none of those. Do you want to switch? Okay, so if I don't switch, I'm still 10% that it's in, my chosen area. It's in 90% in those other doors, but he's then gone ahead and opened 8 of them. So it's 90% that is now in that one remaining door. Let's jump onto the screen and we'll try and visualize this. Each of these 10 boxes is going to represent one of our doors. The rules of the game stay the same. The only thing we've changed is going from 3 doors up to 10. That's it. Now let's suppose, for the sake of argument, we're going to pick door number 1, which is going to be this guy here on the top left. In the original game, you have a 1 in 3 chance of that being correct. We now have a 1 in 10 chance of this being correct. Okay? That's the only difference this time. In the original game, there was a 2/3 chance of it being in the other 2 doors. So by the other doors, we're going to say the ones I'm marking here. So effectively, if I just do this little barrier here, there's basically a 9 out of 10 chance that it exists in the doors that we haven't picked. Okay, now let me just change color. So basically now what's going to happen, the game show host is going to say, right, I'm going to open all the remaining doors apart from the 1 which I know the prize is behind. So he's going to say, I'll open, let's suppose he opens all of these, maybe does these ones, maybe does these ones here. In the original, he opens one other door and says, do you want to switch? In this version, he opens the remaining doors and just says, do you want to switch to the remaining one? Check out these numbers, right? 9 out of 10, 1 out of 10. There was a 1 out of 10 chance we were correct initially by picking this door up here. There was a 9 out of 10 chance it's in this remaining other section. Of that 9 out of 10 section, he's just gone ahead and eliminated all of these remaining doors here. So there is a 9 out of 10 chance that this is the winning door. So hopefully that's a nicer way of seeing it. If you just scale up the problem to say, like, I don't know, 100 or 1,000 doors, you might be, suppose you took the 100 door situation, there's 1 out of 100 chance you're correct straight away. There's a 99 out of 100 chance that it's in the other doors you haven't picked. So he would then just go through and say, I'll open the other 98 doors because I know where the prize is. So that one remaining door, there's a 99% chance it's correct. So all I've done here is that, or just on a smaller scale, but a bigger scale than the original 3-door problem. Okay, so hopefully that was helpful. Now what I want to do is jump into VS Code, and we're going to do a quick Python proof to try and prove whether it's worth staying or switching. Just before we get into writing the code, what I've done in advance is just written down a couple of different steps here. These aren't strictly the way you have to do it, but it's the way I'm going to try and do it. So we're going to set up a way to store 3 doors and their state. So basically, like if the door is a winning door or not, we'll make one a winner. We're then going to store the alternative doors and then present one non-winning door. We'll then ask the user if they want to switch or not. And then, depending on what this is, we can then switch to the other door. We also need a mechanism to keep score. Just something to bear in mind, this is the first time I'm actually coding this, so hopefully it all goes to plan. But I will say I've had a bit of a think this morning about how we can do it, and I think I've got a pretty solid way set up. I'll delete the comments as I go along, just to keep the amount of text minimal. So the way I want to do this, I'm going to say, we'll say doors, is something like this. So let's suppose we have, this represents door 1, it's going to be false. Door 2 is going to be false, and then door 3 is going to be false as well. So what we can then do is we can then just say, like, pick a random key from this and make it true. So that's a way for us to basically make one random door a winner. So there's our doors, our 3 doors and their states. You know what, let's go ahead and print the doors underneath. There we are. False, false, false. Okay, so to make one door a winner, we need to make, well, basically a number between 1, 2, and 3, inclusive of. So to do that, import random as RA. For some reason, I've always done that as RA. I don't quite know why, but yeah, I guess just an out of habit, I suppose. So to make one door a winner, we can say doors, go to this key, and you are now equal to true. And the way we do this is to say ra.randint between 1 and 3. Randint, by the way, it's inclusive of the 1 and the 3. So I'm pretty sure I just deleted doors for no reason. Didn't mean to do that. Let's try that again. There we go. So door 3 is the winner. So we know door 1, 2, or 3, either of those can be a winner. Now what we need to do is to think about how the game show works. We pick one, and then we basically want to say, okay, from the remaining doors, here's one which basically is false. So we'll build it up piece by piece. I'm quite a fan of doing that, so we don't have to do the full thing straight away. You can build up to it iteratively over time. So we'll call it alternatives. And the way you can do this, you can actually do it as, you can do it as a comprehension. So if we did K for KV, so this is basically saying like each key for key value, and there's a reason I've done KV, because we need to use the value in the comprehension, well, the condition part of it. So K for KV in, and this is then going to be doors.items here. Okay, notice how it's made this kind of like a muted color. That's because I'm not using it yet. And let me show you what this looks like up to now. Okay, 1, 2, 3. So this is basically like just the keys. Of course, we're doing it as a comprehension because we can do like some kind of condition here, which is kind of cool. And so this condition is basically going to say like only show the doors that are losing. So we can do if not V. So let's start off with this one. Okay, so let's see what we had. We had true. So with 3 being the winning door, we're obviously not going to be presenting that to the person playing the game. So this if not V basically handles the logic of, as an alternative door, here's one which is not the winning door. It also can't be the door which the player chose, which we don't actually have a mechanism for yet. So let's do player choice is equal to 1 like this. So we'll do if it's a false door and K is not the player choice. To be honest, we should probably do this right at the top, shouldn't we? Let's put this guy here. There we go. All right, let's go ahead and try this. Okay, so this time 1 was the winning door, which we've picked. We've picked door 1. So the only alternatives which can be shown are going to be 2 and 3. Okay, so in this case, we've still picked 1. We'll kind of leave this hard-coded for the time being. 3 was the winning door, so they've given us the only option as 2 coming back. Yeah, that looks fine. 2 and 3. Okay, yeah, I think this is good for the time being. Okay, now what we need to do is basically then just pick one of these. So because this is a list, this could be a list of 2 possible doors or just 1 possible door. So what we'll do is just a little print statement to say like picked. And this is actually quite good to probably visualize it actually. You've picked, we'll do player choice as an F string. You pick player choice. Do you want... And then we'll keep, let's just call this alt, I guess. and then we can do ra.choice of alternatives. ra.choice will just pick a single item from an iterable. So, you know, this could be 1 door or 2 door. It'll just pick one. So we'll do alt. You can do choices and pass in k equals and then choose how many you want. So let's go ahead and try this. And when we run this in a big loop later, we can get rid of it. Okay, let's see. So we've picked 1. Do you want 3? Okay. Yeah, I guess, doesn't add too much to the game, does it, I suppose? But yeah, we can see it here and guess we can kind of visualize it. Let's try another one. Okay, we've picked door 1. Do you want to switch to door 2? And in fact, if we're being super pedantic, what he actually does is basically open one of the doors with the goats behind it, or the non-prize. So we could do like, here's a door blank with no prize. Okay, there we go. Sorry, it's slightly being pedantic, but yeah, there we go. So we've picked 1. Here's a door 3 with no prize. And yeah, and that's the point when then the person playing the game would then try and go ahead and switch. Then what we need is a switching mechanism. I think what I'll do, I'll zoom out ever so slightly. And let's go ahead and do switch equals true here. Basically done those. Well, we would have done in just a second. And then based upon whatever switch is, we then want to say something like if switch. And I think this is going to be the trickiest part to do, like, well, from a coding perspective, because we then want to choose the door which obviously isn't the one we picked originally, and it isn't this one here. So it's going to be something like, just do X for now and then we'll change it. So we'll do door, oh god, no, door, for door, in, it's going to be doors, and it's going to be if, and then we'll say door not in, and then it's going to be player choice. Now when you make this kind of comprehension, zoom in just a touch, when you do this kind of comprehension over a dictionary, this is basically just the keys. So it's basically saying like, go through each key in doors and only include them in this list if the following. And it's going to be if the key is not in player choice or alt, like this here. Okay, let's go ahead and print X. And we've got this set to true, so let's go ahead and take a look. Okay, I think that's worked out quite well. So we picked 1, which is the winning door, and then the game show host has said, yeah, you've picked 1, here's door 3 with no prize, and then because we have switches true, it's then gone ahead and done this. Actually, what we want to do is just do 0 to get the actual item out of there. Let's try another where 1 isn't the winner. Still the winner. Ah, there we go. So we've picked 1, which is, in this case, a losing door. He says, you've picked 1, here's a door 2 with no prize. So yeah, if we switch, we then go to door 3. And, okay, I think that's worked out quite well. So of course, this kicks in if they switch. The last step is just to figure out if they've won or not. So then do if doors, player choice, and just go to our dictionary for a second, because these are going to be like purely Boolean values. You don't have to do like is true or is equal to true. You can just go ahead and do this, and by definition, this will be something true or false. So we can go ahead and do this, and then maybe we'll do wins equals 0, and then do wins plus equals 1, and then just do wins as a F string like this here, just so we can do it as a loop later on, you see. And then there we go. Let's just get rid of this little comment for a second. Okay, let's go through a single kind of instance of the game. Okay, we picked 1, here's a door 2 with no prize, and in this case, we switched to door 3. Okay, so yes, in this case we picked 1, which was a non-winning door. We were presented with door 2, we then switched to the only remaining door, door 3, and we won. And we won again, didn't win that time, won again. So the way we can do this to make this look a bit fancier is to kind of do it inside a big for loop. So if we remove the print statements and construct a big loop to kind of house this logic, then just keeping track of the wins at the bottom of each for loop. So to do that, we're going to have to do a bit of jigging around of this. So we'll do for for underscore in range. It's always better to do for underscore in range if we're not explicitly using the value here inside of this. So it's kind of a nice way of doing it. We'll do 1,000 iterations. And we're going to need to do a bit of moving around here. So we need to keep wins at the top. We're going to need to bring player choice inside here, because This has the potential to be kind of, redefined at the bottom. I think that's it. That's clear. Let's run, in fact, let's try it with false first. Say we're not switching. Okay, 330, 346. So this looks to be, give or take, around kind of 33% of the time. You know what else we can do as well? If we do like another S string down here, we can make like a ratio one. So I'll do ratio. Then inside this here, we can do our wins divided by how many turns there are. We'll just hard code this as 1,000 for now. So if we do this, and let's multiply this by 100, 32.9. I guess this is, I'm going to say win percent like this here. Then do a little one of these at the end. The only thing you might get, sometimes you might get like a horrible rounding. Yeah, there we go. If that does happen, what you can do, it's like a colon, a dot, a 2, and an F. And this will basically format the F string to be just a bit nicer for you. There you go. So it'll always be 2 places now. So let's go and try a few of these, shall we? So it looks like 31%, 30%, kind of hovering around this. Now, this is where the big moment of truth is really, isn't it? If we switch to true, are we going to be in sort of 60s range? I would argue it is, and I'd really hope it is, otherwise it'll be quite embarrassing. Look at that. 66%. Let's try a few more. Check that out. So just by doing the switch, we've dramatically increased the win percentage, which is kind of cool. So hopefully that proves from a coding perspective how this works. One thing I'd definitely suggest as a challenge, especially if you're coding in Python, could you figure out a way to scale this up? So one kind of possible extension to this would be, could you extend the number of doors? So, you could have some kind of variable here of like, doors n is equal to 100 or 1,000 or whatever. Then could you make this problem scale up so you could basically generate this according to however many this is here? If you do so, and manage to get this done in your code, feel free to share it with me in a comment. I'd love to see how you could extend this to include multiple doors. So with the code done, let's head back and do a quick recap. And there we are, guys. That is my run through of the Monty Hall problem. Now, if this is a problem which you find as fascinating as I do you have any special ways where you visualize this to make it easier? Or is there a certain moment you can think of when it clicked and you were like, oh yeah, actually it is better to switch? Let me know what you think in the comments. Don't forget to like, subscribe, whatever. Cheers for watching, guys, and see you all in the next video.